All right, RMS Geometry. Welcome back for another lesson from our book. Today we'll be looking at 10.1.3, which continues our study of circles and specifically looks at chords and inscribed angles. We'll look at a special circumstance where we have an inscribed angle that's opening up to a semicircle. We'll explore how to work with a chord and knowing the radius of a circle. We'll look at two intersecting chords within a circle and see if there's any relationship there. And then we'll also introduce what it means to be an inscribed polygon. So those are the key topics covered in this lesson, along with good practice at the end. Just as you've been doing, please take your time and complete this lesson on your own paper. Reference that answer key attached in Google Classroom if you're wanting to check your work along the way. And then once you've completed the lesson, please come back to this video for a recap of some of the key ideas. All right, guys, good luck with the lesson. I'll talk to you soon. And welcome back. So hopefully that lesson went well, but just to highlight some of the key ideas, let's talk together about each problem here. So in the first one, 10-25, we were introduced to what it means to have a semicircle, which is an arc with a measure of 180 degrees, and then we had to use that relationship to think about some angle measures. So if we look at part A, which has arc QR that measures 180 degrees, so it's a semicircle, we can use the relationship between an inscribed angle and the arc it opens up to find that the measure of angle P is 90 degrees. And that's because our inscribed angle will always be half of the arc that it opens to. So we've got that relationship, and that's an important one because it turns out that inscribed angle that opens to a semicircle will always have a 90-degree measure, which creates right triangles that we can use, and that's what was done in part B. So we're told that UV is a diameter, which passes through the center of the circle, and will always create a semicircle, and that means that angle T is a 90-degree angle. Knowing that and knowing those side lengths, we can then use things like the Pythagorean theorem to find the full length of a diameter and cut it in half to find the radius. So that's really a good relationship that we can use in a lot of situations in circles. 1026 is one I'd actually like to do together. So they gave us circle P that had chord LM drawn within it. They told us the measure of the arc LM was 150 degrees and that the radius of circle P was 6 units. And with that information, we actually had enough to figure out the length of LM. So if we go through and we look at that together, let's look at my crudely drawn circle here. Remember, I'm not using a compass, but you should be if you have one at home. They told us the measure of arc LM was 150 degrees. They also told us the radius was 6 units, and that's an important piece of information because I just drew the radius, PL, and then also PM, and I know those are 6 units. Since angle P is at the center of the circle and opens up to an arc with a 150-degree measure, there's a quick photo shot, then we know that the central angle is 150 degrees. And now we're set up where we can work with this triangle a couple of different ways to find the length of chord LM. So we have two sides and an included angle in a non-right triangle, which means that we could use the law of cosines to solve for that missing side. Another option, however, would be to use the fact that we have an isosceles triangle here. And that lets us find some other angle measures and ultimately create right triangles. So knowing it's isosceles means those base angles are congruent, and by the triangle angle sum theorem, we know we have to add to 180 degrees, which means that each of these angles must be 15 degrees. So we know that, and if I were to draw a height in this triangle that's perpendicular, all of a sudden I've got 3 angles that match in each triangle, so I know for sure they're similar, but I also have that 6-unit side and that shared side that I just drew. So really I could use side, angle, side to come up with my congruent triangles here. And the reason that's important is because then I can just work with one triangle, knowing it's congruent to the other. So we've got a 6 unit side, we've got a 15-degree angle, a 90-degree angle, and then I actually misspoke when I said we knew all 3 angles were congruent. We didn't. That 150, we shouldn't assume that was the same until we'd proven triangles were similar by knowing that the base angles were 15 and we'd created a 90 in each. So now we do know that it's the same, but that wasn't an assumption we should just make. So we've got a 15, a 75-degree angle, and a right angle in that triangle, and 6 units. Now we can use some of our tools to find the missing side. So if I want to know what the length of the base is, let's put an X there. Well, now I'm looking at, okay, I've got the hypotenuse, and then if I'm looking at the 15-degree angle, X is the adjacent side. So I need to figure out what tool works with the hypotenuse and the adjacent. That tool is cosine. So the cosine of 15 degrees is going to be equal to the adjacent side over the hypotenuse. Now I can use my calculator to find the cosine of 15. If you're like me and you're using Desmos calculators or other online calculators, it's really important that you check and make sure you're set to degrees on that calculator. Just like we did with our graphing calculators, although those should already be set, you need to have degrees to use these trig tools correctly. So we said the cosine of 15 was equal to x over 6. So I could do 6 times the cosine of 15 degrees to get an answer to show up. They give us 5.7955. Let's call that 5.80 when we round that. So x is equal to 5.80 units. If I know x, then I can actually multiply that by 2, since that was only half of the chord LM, and get my final answer. So LM will have a measure of 11.6 units. And that's how we can work through problems like that if we know the radius, and if we have an arc measure or a central angle. We can always use a similar process to that. In 1027, this was an important fact that showed up. So they gave us intersecting chords, and the idea was using vertical angles at angle or at point E, and then also knowing that DBE and ACD open up to the same arc. Excuse me, I should say DBA, since point E doesn't actually go to the circumference of that circle. But DBA and ACD open to the same arc. They actually have the same measure, even though it looks like they might not. So right away we see angle-angle similarity between triangle DBE and triangle ACE. That lets us use ratios and scale factors to work between different side lengths. So that's why you can find missing side lengths as you go through 1027, is because you have similar triangles there by angle-angle. 1028 introduces an inscribed polygon. For this one we have a quadrilateral, and you may have noticed when you have opposite angles, well, those opposite angles of an inscribed polygon open to opposite arcs. So those arcs should always add to 360 degrees. A 100-degree inscribed angle is going to open to a 200-degree arc, which means that the remaining arc, BD, is going to be 160 degrees. And the 160-degree arc has an 80-degree inscribed angle that'll open to it. So those are the kind of things that you can think about as you go through. 1029 was an opportunity to practice using some of these. You can check your answers in the answer key there, and then if you have any questions, be sure to use the office hours time from 9 to 11 to ask questions that I'll get back to right away, so we can help you feel confident with these new ideas related to circles. Once you finish this whole lesson, please do the review and preview. for the homework. Just like always, take a picture when you're done and submit it on Google Classroom to get credit for that assignment. All right, guys, good luck with the work, and let me know if you have any questions.